In the 1970s, severe global oil shortages forced automotive engineers to seriously imagine a world without combustion. Gas lines stretched for miles, and filling a tank suddenly became a heavily rationed luxury. The immediate, pragmatic response was to simply rip the engines out of existing vehicles and pack them full of batteries, a strategy tested on models like this experimental Bedford-Lucas electric van. But these early conversions immediately collided with a rigid physics constraint. Standard lead-acid batteries have low specific energy. To achieve any meaningful driving range, engineers had to load the chassis with thousands of pounds of heavy lead plates. This chart outlines the resulting bottleneck. Look at the curves for the lead-acid units. There is a direct inverse relationship between specific energy and specific power. The moment you pack enough mass into a van to make it travel a decent distance, you severely degrade its ability to accelerate or climb a hill. Basic lead-acid chemistry trapped early designers in an unwinnable physical compromise between distance and speed. Compounding the massive weight of the batteries was the inefficiency of the drivetrain itself. These conversions relied heavily on primitive, heavy DC series-wound motors. As you can see in these circuit diagrams, controlling the speed of those motors required crude rheostatic control, which involved splicing field diverter resistors directly into the electrical path. Because these resistors regulate current by restricting it, precious battery energy is quite literally burned off as wasted heat just to modulate the flow of power to the wheels. To build a vehicle capable of rivaling a gas engine, the industry had to abandon both standard battery chemistry and these brute force DC motors entirely. Solving the range problem required a shift toward radical, high-temperature chemical reactions. This Zebra cell provides energy density for long distances, functioning at a molten 350 degrees Celsius. Inside, a solid ceramic partition separates liquid sodium and sulfur, acting as an electron barrier while allowing sodium ions to migrate across. Operating at those extremes demands intense packaging. The cells must be sealed inside double-walled, vacuum-insulated steel boxes, simply to contain the molten core and protect the rest of the vehicle. These extreme thermal environments provide the necessary energy for distance, but their internal chemical reactions are inherently too sluggish to provide the rapid burst of power needed for sudden highway acceleration. Engineers explored continuous energy generation as an alternative. Vehicles like this Ballard fuel cell bus sidestep the thermal battery issue entirely by carrying liquid fuel. Inside, a catalyst splits hydrogen molecules. Proton slips through an exchange membrane, generating a continuous electrical stream without the massive weight of a thermal battery. Yet, fuel cells and thermal batteries share the exact same flaw. The chemical reactions they rely on simply cannot scale up quickly enough to deliver instant physical power. This diagram illustrates an electrostatic solution, the electric double-layer capacitor. By avoiding chemical reactions altogether and relying purely on physical absorption, ions snap directly onto polarizable carbon electrodes, allowing for an instantaneous, massive discharge of energy. Another approach uses kinetic storage. Vacuum-suspended carbon fiber flywheels violently spin up to absorb kinetic energy during sudden braking, releasing it just as fast. Achieving peak vehicle performance requires a paradoxical hybrid architecture. Designers pair deep, slow-reacting chemical or thermal systems for marathon range with these fast-acting kinetic or electrostatic systems for sprinter burst power. Generating massive amounts of hybrid energy is only half the equation. The final engineering hurdle was learning how to seamlessly sync these disparate power sources and deliver them to the tires without bleeding off heat. The answer was the three-phase AC induction motor, the highly efficient successor to the heat-wasting DC drives of the 1970s. Instead of physical resistors, modern controllers use high-voltage transistor switching. Firing in a rapid pulse-width modulation sequence, they generate a rotating magnetic field that effortlessly drags the central rotor forward. Because this electromagnetic slip pushes the rotor without direct physical contact or resistive heat loss, the overall drivetrain efficiency reaches up to 96%. The arrival of the first highly optimized, purpose-built AC induction vehicles signaled that engineering had moved past the limitations of simple combustion engine conversions. Abandoning internal combustion engines and bulky DC motors created new packaging opportunities across the chassis. In this EV1 cutaway, engineers used ingenious coaxial transaxles, passing the drive axle directly through the hollow AC motor to save lateral space. Eliminating mechanical differentials clears the structural spine, making room for the massive, high-density thermal battery packs required for serious range. The modern electric vehicle operates as a rolling physics laboratory. By balancing the paradoxical demands of energy and power through molten thermal boundaries, spinning vacuums, and tightly controlled electromagnetic fields, engineers have optimized the specific mechanics of transportation for a post-combustion world.